Good morning. Thank you for the organizer to give me a chance to present some aspects of our work. And also thank to the speakers just before and Alexis because they introduced nicely the inorganic nanoparticles for the use for medical application. And what I like to show here is a little bit something, not all the applications, but I'll go one step back and I will go more a little bit, and as you have seen in the title, to try to explain a little bit better maybe on the long term what happens with the particles. So the iron oxide nanoparticle, for example, is interesting because, as you have seen before, it's used today in MRI as contrast agent in MRI. It's coated with dextran, goes to the liver, and is in this sense passive targeting because it goes more or less automatically in the liver in 5-10 minutes. But also if you bring it in stem cells, they're interesting for cell tracking, or we have seen for drug delivery, especially if you apply external magnetic field gradient, so you can localize the particle in one area. And additionally, if you, for example, use the hyperthermia effect, means the heating, so you can use it in combination of cancer treatment by heat, hyperthermia, or what we have seen before, also we can use then the heat to release, control the release of the drug, for example. So it's a very versatile particle, but for sure, because they are paramagnetic, you can also use it for, and most of you maybe if you're working in biology, are using it for cell isolation and other separation methods. Now, what I like to do is a little bit to discuss more, because what we also have seen just before is if you have a different coating, you have a different behavior. You have lactose and gold, they go in the liver. If you have glucose, they go in different organs. And if you are speaking about now here about targeting, we have to also to see how the coating of such particle, and all the particles are always coated, how the coating can influence the targeting, the passive targeting, and if you add additionally targeting molecules like epitopes, antibodies, and as you've shown before, then maybe how we can do it more controlled. So what we have done during, let me say, the last 5 more years, we are working with iron oxide, the core particle, iron oxide, Fe2O3, and we have now different shells on the particles. We have one with organic, PVA, polyvinyl alcohol, with positive functional groups, negative functional groups, or we have then inorganic coating, silica with amino groups, titania and gold, on the shell. That means what we have here is a system where we have always the core iron oxide, and we can use always magnetic forces to do separation. We can use MRI to follow the particle in the body. So we have here, we use the iron oxide as a tool, and to investigate the coatings. You see also the charge of these different particles. They can be in the area of, let me say, neutral, at pH 7, or they can be positive or negative, depending on the coating. What I like to show is the results coming out from a thesis from June. This is a little bit difficult picture, but I like always to show it, even you cannot read it. But what you see here is different colors. What you see here, these are the organic coating. These are the iron oxide particle coated with polyvinyl alcohol with positive charge, neutral, and negative charge. If you look only on this part, if you bring this in cell media and you take it back, separate it back, and analyze all the protein which are on the surface, this is one part. The table is much longer, but this is the most important part. What you can see very easily, and is more or less also known, that in the positive charge particle we have a lot of different proteins on the surface. And on the negative charge particle we have very low numbers of different proteins on the surface. This is the first thing. And what we also see here is that we have a huge number of proteins detected. That means not one of the particles have the same composition. Yeah, it's not possible to have 50 proteins on the surface of a particle. We could have maybe 5 to 10, because this is purely from the size. It's not possible. That means also that the particle in cell media, if they are look on uptake, we have always a different coating. Each particle must have something other things. Yeah? But also what is also important from the color now, the red one are the most abundant proteins in the media. Yeah, we have defined 6, and only 3 of these are really on the particle, others not. This means we have not normal adsorption. Yeah? Thermodynamically, it means a lot of these proteins is in the media, so we have a lot on the surface. We have here also specific adsorption. Yeah? And even we have some particles here, you see here, and if you go now to the inorganic coating of the particle, we have here positive, negative charge, and both are silica, but different functional group on the surface. You see here again a negative charge as here, similar negative charge, but this is silica, this is polymer. We have a different answer of the particle to the media. And then if you go then in titanium and gold, again, it's different. Yeah. So this is a very complex picture, and it's very difficult to understand this in detail. If you look now in the literature about the protein adsorption on flat surfaces, yeah, we know that particles have homogeneous charge distribution, protein not. Then we have a charge regulation mechanism. The charge of the proteins is changing with the environment, yeah, a local electrostatic environment. Yeah. Then at high ionic strengths, what we have in our cell media, so the normal colloidal theory is not valid. Yeah? We can have attraction of similar charged particles occurs. So positive is an attraction move. Positive, overall positive charge proteins on a positive surface can have attraction. Yeah? It's shown years ago. Yeah? And what is also that near surface exists an uneven distribution of the ions. This means, because the proteins are larger than this layer of the ions, yeah, the double layer, yeah, we have on one side of the protein other pH than on the other side. Don't forget, the protein has 5 nanometers. Our particle are in the area of 20 nanometers. The layer where we have the electrolyte concentration different is maybe in the area of 2-3 nanometers. Yeah? So all these affect then the concentration, the adsorption. What we can do is look on the isoelectric point of the particle and the pH where we are, and on the difference of the protein and the pH of the media. This means we have we can have a negative charge on the particle, a negative charge on the protein, or we can have a positive charge on the protein and one negative on the particle, and so on. Yeah? And if you can define then, let me say, an interaction index, yeah, which gives very roughly an idea if you have attraction or repulsion overall between the proteins. Yeah? So if this value is, for example, positive, this means one part is both have the same charge, and if this value is negative, then we have different charge. This comes from colloidal chemistry, the definition of negative and positive. Yeah? And this is the result. If you are looking now on all these results, what we have, yeah, different charged particles. Yeah, here are these with the polymers. Here are these with the inorganic coating. What we see is that the negatively charged particle, okay, you have less proteins there, and we have always the same charge. So on a negative particle, negative proteins are found. If you go in both cases, in inorganic and organic coatings, if you have, let me say, particles with zero charge, around zero charge, neutral, yeah, we have still the, let me say, a slightly positive charge particle. We have more or less positive proteins on the surface. We start here with the opposite charge. And if you go in the positive charge particle, here you see here, we have a huge amount of negatively charged protein on the surface. Here we can say the colloidal function. If you look on the overall charge now of the coated particle, they are always negative. Yeah? So what we can say now, and if you look now here, the next step is now, so this means, sorry, if I go back, so what we can see here is more or less the influence of the adsorption of the proteins. We know which proteins are on the surface. And if you now think you know more or less what happens in the system, if you do now the following experiment, we have the in vitro, show you before, with the same serum, rat serum for example, and then you put the particles, you put the same charge, but the other particles in rats, in intravenous injection, and you take after 15 minutes back the particle, yeah, out from the bloodstream, yeah, and you look then on the proteins which are on the surface. We see different proteins, the same particles, yeah, the same blood or serum, both rats. And what we can see here is now that in vivo, so-called in vivo, the experiment was done then finally outside, but this particle 15 minutes in the blood circulation. What we can see very clearly is here we have a shift of the type of the proteins. What we have mostly is a shift to the low molecular weight proteins. Or in other words, if you go in more in detail, I don't show it because of time, but we have different proteins on the particle. Now this is then the question, means then if you do tox tests or uptake tests in vitro, has the real relevance regarding in vivo tests later on applications. Yeah, from our point of view, it's very, very difficult to make any conclusion from in vitro tests to in vivo tests because you don't understand really what happens with the particle. Because the particle, they are always covered by this protein corona, and the cell sees always the protein corona. They don't see the particle at the end. So you see it also now in the uptake mechanism. You see here the negatively charged, not a lot. The positive have a lot of particles inside. Yeah. And this is, for example, if you have use here macrophage or monocytes, you can load these monocytes very rapidly with the particle, and you can transport it to the site of inflammation. So we use this method, for example, for imaging by MRI, the site inflammation of in joints. You see here now the biodistribution, also shown before, but here now you see now the same particle, the same coating. Beside we have different functional groups on the surface. That means different proteins on the surface. So the positive, with a lot of different proteins, they are in the liver. In 15 minutes, the half of the particle amount is in the liver. But in the negatively and positively charged, neutral and negative, sorry, you see the most is still in the serum and in the circulation. It means with the charge, we can control or we can influence, let me say like this, we influence the protein composition. With this, we can influence the biodistribution of the particles. So protein absorption in complex media depends on the charge and chemical composition of the shell of the particle. So we can influence these two. Negatively charged particles absorb much less proteins than neutral or positive charged. Then the protein corona composition is very different in vitro compared to in vivo. And then the biodistribution depends on the protein corona, and this depends from the charge of the first particles. And so we can also show that coated and subarachnoid particles are useful tools to mimic the colloidal and biological behavior of inorganic and organic particles, because you have only the shell, and if the shell is the most important parameter. With this, I'd like to thank you for your attention.